So summary of the results. So first thing they have shown is that TPU is 15 to 30 times faster than the contemporary GPU or CPU. And if you see the efficiency, then which is expressed in terms of number of operations per watt, that is 30 to 80 times higher for TPU compared to CPU or GPU. Okay. And TPU version 1 uses DDR3 memory. If you were to replace it with GDDR5 memory, right, then it will further increase the performance of TPU and it will further raise the TOPS per watt metric. Okay, so first of all, so the whole point is because TPU is so simple, that's why it achieves much better performance and much better, energy efficiency. Okay, but there is also some limitation. So one limitation when we discuss this result. So I will just first discuss this. So before we discuss this, one point you have to remember is that in TPU, right? For TPU, they are doing the operation in 8-bit. Okay, whereas for Haswell, right? Haswell they are doing floating point operation. That means for CPU and GPU they are doing floating point operations. So that's why this gives an additional advantage to the TPU. Fine. So when you see these results, you have to understand the caveat also. The limitation, first limitation is that CPU and GPU, their results are for FP, and for TPU, the results are for 8-bit integer. So definitely integer is faster plus 8-bit integer is faster than 32-bit floating point. Second point is that they have taken K80 GPU, which has support for reliability. And but there are other GPUs which they should have tested, where the throughput is much higher, even of the same year. So this study was, I think, in 2016. So even in this year, 2016 also, we had other GPUs where the performance was higher. Okay, so sometimes these performance comparisons, because they are done by the industries themselves, there could be some bias. It's not like that deliberate wrong, but there could be better way of doing the experiments. So these 2 points you have to remember. Now let's see these results. So one more thing I want to remind you is that 61% is for MLP. That means Google's data centers, 60% TPUs are deployed for MLP. Because in 2016, MLP was very prominent. LSTM was for 29% and CNN is 5%. Now let us see first this. So MLP, TPU is much better. Fine. On MLP, so these results are normalized to CPU. Okay. On RNNs, right? Or RNNs, CPU is quite good. Okay. On RNNs, CPU is quite good. For CNN, again, TPU is very good. So TPU is good for MLP and CNNs, but for RNN, CPU is quite good. So the reason is in RNN you don't have a lot of parallelism, and right. So RNNs they don't have massive parallelism, so that's why CPU is good. Whereas for MLP and CNN you can have a lot of parallelism, and that's why TPU is good. Okay, this is the weighted average. So this weighting is that the point is here 61% weighting is given for MLP, 29% weighting is given to LSTM, 5% weighting is given to CNNs. So I hope this part is clear. Any questions here? No questions? Okay, let us go further. So now let us see this part. So here we will see why certain value of performance is obtained for those applications. So first of all, highest performance is obtained for CNN 0. See, remember, the peak is 92, right? If you see these results, the peak flop we can get is the peak tops. That means tera operations per second we can get is 92, right? That's the max we can get. We can't get more than 92. So out of that 92, CNN 0 achieves 86, which is very good, right? And why it achieves that? From this whole slide, can you tell me why is it that CNN0 achieves such a high value of performance? We discussed this last time. If anybody remembers, can they please tell? Ashish? Can you see this whole slide? Last time also I asked the same questions. One student was able to answer. I'm repeating the same question. If you remember that. Argya?
Because of high AI?
Yes, yeah, you can see the ops per weight byte is highest for CNN0. That means it has very, very high arithmetic intensity. Okay, because it has very, very high arithmetic intensity, that's why here the matrix unit always remains busy. For each weight that you fetch, you can do so many operations. Okay, so you're very effectively hiding the memory latency. That's why you can achieve very, very high performance. And of course, the weights are very less in number, and those things are there. But main reason is that ops per weight byte is very high. That means arithmetic intensity is very high. Second highest is for CNN1. So let us see CNN1. CNN1 has 14. So here in CNN1, there are a lot of max which remain unused. Right? Lot of max. That means lot of max that remain unused. So that probably could be that your size of MAC array is 256 cross 256. So, but if your multiplication that you have to, if the matrix multiplication you have to perform, the size of those matrices are much less than 256, then some of the max will remain unused. Right? So that's why you can see for CNN0, there is no unused MAC. Right? Here that number is 0%. Whereas for CNN1, so many max are unused. 23% max are unused. And you have a 256 cross 256, that means you have 64K matrix. Out of this useful max here, it is 78%, but here it is only 22%. Okay, percentage of the time you are able to you use those MAC units, that is 22%. Fine. Now here these are the stalls due to memory. So see, the point is we are fetching the weights from memory, and while the weights are being fetched, the systolic unit does the matrix multiplication. So we try to hide the latency of memory access. But if the weights don't arrive in time, then matrix unit have to stall. For CNN0, matrix unit does not have to stall at all. But for other neural other networks like NLP, here more than half of the time they are stalling. That means weights have not arrived. Wait. I'm asking, okay, send the weights. Weights are not arriving. Okay. So this LSTM is same as RMN. So here we are writing LSTM, in this we are writing RMN. They are same. Okay. So here you can see more than almost here 60% of the time matrix unit is idle. So if matrix units are idle, how can you do any compute? That is idle. Your compute units are idle, right? And there are other types of stalls. That means read after write, there are hazards. In pipeline, there are hazards. If you have studied architecture, you will know, but otherwise fine. Now input data, that can also cause a hazard. I mean, that can also stall. That can also lead to stall. No, not hazard, that can lead to stall. That means you have input data coming from the activation buffer. Let us go back and see this. So back and forth, if you see this figure, you will understand the whole of TPU architecture. Here, see, weights are coming from the top, right? Weights are coming from the weight FIFO. Although the weights are stationary, but for every layer you have to fetch the weights, right? And the activations are coming from here. That means input is coming from here. So there could be some delay due to delay in the arrival of inputs. There could be some delay because of the delay in arrival of the weights. Fine. So each of these could contribute stalls. Now let us see. So array active cycles, this is very, very high for CNN0, but for others it is much less. So this very nicely explains. So now the biggest bottleneck you can see is that wait stall cycles are high. So in the TPU version 2 and 3, they have reduced these stall cycles because they have improved the memory part, right? They have improved the memory bandwidth so that stalls due to memory are reduced. So now you see how Roofline we discussed, right? Whichever is the bottleneck, that is the bottleneck you need to answer. So TPU has abundant amount of compute, but memory is slow, right? You request some data from the memory, the data does not arrive in time because memory bandwidth is low. So where you need to work on, you need to work on improving the memory bandwidth. And that is what they have done in version number 2 and 3. Okay, so any questions based on what we have discussed till now? No questions. Okay, fine. And you can see that other networks achieve very less amount of, performance compared to the peak. So compared to the peak that TPU can perform, can give you, you achieve very less. But even this is better than what GPU offers or what CPU offers. So this now here is the Roofline model for three processors. This was the actual performance without Roofline model. That means without comparing the peak performance. Here is just the actual performance, and here we are showing the peak performance compared to each of their Roofline models. So here this blue one is the Roofline for the TPU. This one is the Roofline for GPU. This is the Roofline for CPU. So here you can see all TPU. These are TPU. For TPU, they have shown the stars. They think they are the stars. Okay. For KAT, they have used triangles. For Haswell, they have used circles. So all TPU stars are at or above the other two Rooflines. So here you can see all the 6 stars. They are at or above the Roofline of other. That means whatever others can, whatever you can get, even if you do any optimization on CPU or GPU, you can never achieve more than the Roofline, right? The Roofline is the highest you can get. But even higher than that is the performance you get on TPU. Of course, with the limitation, you have to remember the limitations they have. Fine, because they have so many limitations. That's why their results cannot be considered as perfect. But still, assuming whatever they presented is okay. So here you can see these are the stars are for the results of TPU. These circles are the result for Haswell. That means the CPU. And the triangles are the result for GPU. So for some of them, GPU is very poor. Right here, why? Because arithmetic intensity is so low. Okay, this star is for, I think, MLP 0. So for MLP 0, the arithmetic intensity on GPU is very poor. Okay, is it fine? Shall we go ahead? And here are some numbers based on performance per watt. I'm going to skip this slide. Again, they show that their results are better than both CPU and GPU. Okay, so now this concludes our discussion of TPU version 1. Okay, so I will show this slide later on because right till now I have not discussed the Brainwave. But let us quickly see this. Then again we'll come back to it. So Brainwave is the Microsoft's architecture. Brainwave is implemented on FPGA, that is TPU version 1 is an ASIC. All the TPU versions are ASIC. Okay. Now here we have 8-bit integer, right? Remember, in TPU version 1 we have 8-bit integer. In Brainwave we have 8-bit floating point or 9-bit floating point. Fine. So here that is the difference. It is floating point, here it is integer. Now here weights are stored off chip, right? That weight FIFO. Here, the weights are stored in DRAM, right? So here the weights are stored off chip. Here the weights are stored on chip. Here the batch size is used is between 8 to 200, as you can see here. The batch size used is between 8 to 200. Whereas in Brainwave, the batch size is just 1. Okay. Now in TPU we are doing matrix multiplication, right? How are we doing matrix multiplication? Anybody tell me, please?
Systolic arrays that we have.
Yes, very good. Yeah. In TPU we have systolic arrays so that we can directly do matrix multiplication. But Brainwave does not have systolic array. Brainwave just had dot product units. So in Brainwave, we are multiplying matrices with vector. Okay, both of them use CISC ISA. Here number of max is this. Here number of max is 80,000. So here, Brainwave architecture, because it is implemented on a particular FPGA. So depending on that FPGA, this number will be decided. 80,000 will depend on each FPGA you have. If you implement it on a better FPGA, your number of max can improve. This performance will also improve. This will also improve. This will also improve. This will improve. This will change. So these all depend on the FPGA. Fine. These all depend on the FPGA. Okay. So FPGAs run at very low frequency. So here it is only 500 megahertz. DP also does not run at very high frequency. It is still just 700 megahertz. But highest throughput you can get for any application that they have shown. Here it is 86. Here it is 39.5. But again, applications are different. So these numbers are not directly comparable. Right? It is not that I have compared the same application on this and this. No, this is not an apple-to-apple comparison for the throughput. This is just some number which I have given just to give you an idea. Okay, fine. So don't take this as ultimate number. But in general, ASIC will always give you better performance than FPGA. Okay, ASIC will give you better performance than FPGA in general. Okay, so now the next question I will ask you is that why should we use FPGA then? Let us ask Hemkant or Sagar. Hemkant or Sagar, can you tell me if ASIC always gives you better performance, why use FPGA at all?
Sir, in FPGA we can reuse it again.
Yes.
For some, we can optimize
it and again
reuse
it. Yeah, and the costs are much less. In ASIC, designing ASIC takes a lot of time and energy. So only big companies can afford it. Small companies cannot afford it. Right? Suppose here if we start getting, ASICs, it will be too much cost. We can't even tolerate. We can't bear those costs. So remember this pluses and minuses of each option. Now the feature size of this Stratix 10 is 40 nanometer. Here TPU version 1 is designed in 28 nanometer. Here the power is 75 watts. Here for a FPGA full utilization is 125 watts. Again, this all depends on actual FPGA. And here TPU version 1 has total memory of 28 megabytes. Here it is 30 megabytes. Okay, any questions here? Let's go to version 2 and 3. So in version 1, we support only int 8, right? But version 2 and 3, they also support brain floating point 16. So I hope you remember what is BF16. So now next question to I will ask. So we have BF16 and we have FP16. So are they same or are they different? Shubhanshu or Srinivas, are they same or are they different? BF16 and FP16, are they same or are they different? Shubham, Sai Vikas.
They are different, sir. Like in exponent BF16, the exponent bits will be much lesser compared to B16. Also, exponent bits are same, but mantis bits are different.
No, wrong answer. Anyone else? Shubham, Srinivas, Shubhanshu, Priyansh, Sagar, Naveen. Narendra, Mohit, anybody?
So
Yes.
BF16 is different. It has the capacities, I think, equal to BF32, sir. The addressing capacity, because of its
Addressing capacity is not the right word. There is a different word. You are in the right track, but addressing capacity is not the right word. What is the correct word?
Sir, Mantisa bit is less
In what?
So the
in
exponents are
BF16.
same as of BF32, sir.
And the exponent will be same.
So the range is,
No,
I think,
how can
the range
exponent is
becomes
same to
more.
what? Sagar, exponent is same to what?
Sir, exponent is same to FP32.
Yes, yeah. So there are three things. One is FP32, which has 8 bits of exponent, right? And BF16 also has 8 bits of exponent. Whereas FP16 has total of 16 bits, but only 5 bits are for exponent. So Sai Vikas, what you told probably, you were saying exponent The way you were answering, it appeared to me you are.
No, sir. I'm saying exponent is same for like I didn't mention FP32. That's my.
Yeah. So that word FP32. So I will assume it is FP16. You are assuming that
sorry.
you are equating the number of exponent bits between FP16 and BF16. Right. So see, there are multiple optimizations that in each accelerator you will see that some optimization they are doing is what is the compute unit, what is the precision they are supporting, right? So all these optimization you will see. So and what is the memory they have. So these are the crucial features you have to observe, right? So here and so if they only support integer, they cannot be used for training. If you are using an accelerator for training, you have to have support for either FP32 or at least BF16, one of these two, right? Because with FP16 also you get very less range, which is not sufficient. So if you want to use something for training, you need to have either FP32 or BF16. For inference, you can manage even with int8, right? So for example, if time permits, I will discuss Hexagon's DSP. Hexagon's DSP has support only for fixed point. It has no support for floating point. So it is used only for inference. Yes, Sagar, you have any question?
Yes, sir. Actually, this is related to floating point.
Yeah.
Out of means floating point 32, FP32 and BF16, so which representation is better? Means
which is better? Yeah. So see, that's a good question. Actually, see if you want, whenever you design an accelerator, first thing they will see is what is the throughput. If you want to show higher throughput, usually FP16 will give you higher throughput because you can do 2 computations. FP16 is narrow, just you have to operate only on 16 bits. In FP32, you have to operate on 32 bits. So BF16 will give you higher throughput. But the range is also same, right? BF16 has same range as FP32, but precision is lost in the BF16. So that's why one accelerator I will show that is IPU, Intelligence Processing Unit from GraphCode. They don't support BF16. They support FP16 with some optimizations. Right? They support FP16 and FP32. So although the BF16 is definitely more popular than FP16, right? But the limitation is that because you have so few Mantissa bits, you have a lot of approximation. So out of BF16 and FP32, definitely BF16 is good because you don't lose much, but you get to have higher throughput.
Sir, also we have to consider this less number of bits, right? Means we can.
Yeah, because you have less number of bits, you need to operate on less number of bits. Yeah, so you can get more throughput.
Okay.
Any other question? So, okay, so out of them, TPU version 3 requires liquid cooling. Okay, so version 2 and version 3 they are useful for both training and inference, but obviously they're primarily for training, but you can also use for inference. No, there is no problem. Now, TPU version 3 has DDR3 memory. So if you remember, DDR3 has very less bandwidth. So we thought, like here we said, right, can be if we were to use GDDR5. So because GDDR5 has higher bandwidth, so instead of GDDR5, they have just moved to HBM. Okay. Now in version 2 and 3, they have moved to HBM, which has 20 times higher bandwidth than TPU version 1. Fine. Now this is the design. So here they have MXU. So TPU version. So now version 2 and version 3 they are quite similar. That's why we are discussing them together. Version 4 is quite much different. So we'll discuss that separately. In version 2 and 3 there are a lot of similarities. Okay. So here in TPU version 2 we have only one MXU, and in version 3 we have 2 MXU, one here and one here. Okay, now they also have core sequencer and transpose unit that we will not discuss. So now you can see there is one vector unit for doing vector computations, and this is the matrix multiplier for doing matrix computations. Okay, so I will again when I discuss the next accelerator, I will again compare with this one. So every time I discuss a new accelerator, I will always compare with the previous ones that you know. So you will get a very good, by the end of this course, you will get a very good idea about how different accelerators are designed, what are the desired features, what are not desired features. Okay, so here first thing we did is we changed from DDR3 to HBM so that we can get more capacity, but not just more capacity. That is not the most important. The idea is to get higher bandwidth. The floor plan of TPU version 2. So here we have 2 MXUs. Right. So now one thing was, what was the size of systolic array in TPU version 1?
256 into 256.
Yeah, and here it has been reduced to 128 cross 128. Okay, so that is one change you have to make. That is one major change. I mean, in one way it is a small change, but why they did it, that's a major reason. So here now. So I will go forward. Now, what are the other things? This I will not much discuss. Let us go forward. So now TPU version 3 also has a large 2D systolic array called MXU. Okay, but the difference is that TPU version 1 had a 256.256 systolic array. Now, if you have a smaller dimension of the matrices, then it is not fully utilized. Or if you have sparse lineage. So to alleviate this limitation, TPU version 2 reduces size of systolic array to 128 cross 128 and doubles the number of MXU. Okay. So total number of max is reduced from 64K in TPU version 1 to 32K in TPU version 2. Now next question is, okay, why not go to 64 cross 60? Yeah,
sir,
yes please.
Sir, can you please show the previous slide once, sir?
Okay.
Sir, here it is 128 by 128 by 16 bits. Okay, sir. Sorry,
Yeah,
sir. I thought it is 3 dimensions, sir.
No, it's not 3 dimension. It is 16 bits because the data is BF16.
Okay, sir. Okay, sir.
Now
Sorry,
see,
sir.
this is one core. So every core has one MXU. So just I'll show you some numbers so that 1 minute. Here first let us see this part. Then I will come back to that. See here, how many cores we have? In each core we have one MXU. Here, right? In TP version. So right now let us forget TP version 3. Let us just compare these two. So in TP version 1 and version 2, every core had just one MXU. And TP version 1 has just one core, whereas TP version 2 has 2 cores. So here, what I've shown you is this is just one TPU core. One TPU core of version 2 or version 3. And here, these are the 2 cores. This is one TPU core, this is one TPU core. So each core has one MXU, TPU version 2, and we have 2 cores. So total we have 2 MXUs. Okay, and these 2 cores are connected by this intercore interconnect. Okay, and here we have HBM port through which we connect to the HBM memory. Fine. Okay, so let us go further. So now next question is, we reduce from 256 cross 256 to 128 cross 128. Now why not go further down to just 64 cross 64? If you remember, what is the size of matrix multiplication unit in the tensor core? What size matrices does tensor core multiply? Dwara Ranjan, Anubhav. Please don't forget all this. The whole idea of discussing all this etc. is so that you have everything at the top of your brain. Anybody remembers in tensor core what was the size of matrices we multiplied? I mean, in a single cycle. Yes.
So 3 cross 3.
No, it was not 3 cross 3. Suman, Vishnu Chaitanya, Mohit, Akhil,
4 cross
Aditya.
4.
Same 4 cross 4.
So Mohit.
Mohit. Yeah, that's correct.
Yes.
Yeah, in tensor core it was 4 cross 4.
Supports in 4 by 4.
Sorry?
Sir, you already told, sir. I think it supports int 4 by 4, sir.
Yeah.
The diagram.
Yeah. Each matrix there was 4 cross 4, and we can multiply to 4 cross 4 matrices in a single cycle. And here, what is the size of systolic array? 256 cross 256. So here, TP version 1 used a larger systolic array, right? Because the TPU has only one such systolic array. Whereas in that GPU that we discussed, I think that was First we discuss Volta, then we discuss Turing, right? So how many tensor cores were there? 640 tensor cores were there, right? Volta GPU had 640 tensor cores. Here we have just one core. Here you can see we just have one TPU core. So that's why you can see this is larger. So we will like to combine multiple methods multiplication if possible, and then run all of them. So these features you have to observe. Then you will become an architect, computer architect. Okay. So now next question is we could go, to from 256 to 256 we went here. Why not here? And why not 4x4? All these are possible good questions, right? So now first of all, if you go to 4x4, you will have lot of small units, right? So area overhead will become large because with every core you have a lot of peripherals, right? Those peripherals take a lot of area. So although using a smaller size MXC would have improved utilization, but area overhead also becomes high, right? You have so many, so every time you increase number of cores, you will have a lot of interconnects between them. These interconnects keep on taking more area. Fine. So Gaurav Verma, is it fine? Everything you are able to understand, Gaurav Verma? Okay, let us go for it.
Sir, is Gaurav?
Gaurav Verma, there is another, I know. I mean Gaurav Verma only. So Gaurav Verma, is it fine?
Yes, sir.
Okay, so because you are expert in this area. Okay. Now, again, TPUs are meant to work with larger batch size. So remember, when I come to Brainwave, there the specific goal is just work with a batch size of 1. Whereas here, in training, we use large batch size. Okay. So here, that's why the batch sizes are large to achieve high throughput. Now, training uses multiple processors. So use of, we are using 2 cores per chip in TPU version 3. I mean, both in version 2 and version 3. Here we are using 2 cores per chip. Right? We are using 2 cores per chip. So because we have just 2 cores per chip, so the point is we are not having a single large core. Because see, if you have a single design, a single monolithic design, then it has high latency. But instead of 1 core, they went to 2 core, but they did not go to 4 or 8 cores because having too many cores makes it very difficult to program. Okay, having so many cores makes it very difficult to program. That's why they just stopped at 2. They went from 1 to 2, but they did not go any further. So that means it's all trade-off. Having 1 core has its own advantage, 2 core or 4 core have their own advantages, disadvantages. So here is the comparison. This is the Volta GPU. Okay, this is the Volta GPU. So what is the, it supports 8-bit integer. Here it supports both 16-bit and 32 bits. But as you can see, if you were to operate it, so I think Sagar was just now asking this question. If you were to operate on 32-bit, you get very, very less throughput, not just half, but much, much less than half. So is it fine, Sagar? Did it answer your question? That's why they all showed their throughput results on 16-bit. Now here, this is the because you also have to design them for supercomputers. So TPU version 1 is for inference. Inference is a very, very small workload. But when you are doing training, you have to use many, many chips because training a neural network takes a lot of chips. So you have to connect them. So that's why they're also mentioning maximum chips per supercomputer. So for version 3, you can connect up to 1024 chips and get very high throughput. Here, the TDP just 75 for each chip. Here it is 280. And for version 3, it is 450 watts. Okay. So how do you manage this? How do you manage this 450 watt? How do you cool it? Anybody can answer? How do you cool this 450 watt power consumption?
Sir, you said liquid cooling.
Yes. Yeah. Good. Yeah, liquid cooling. Yeah, because it's so much power consumption, you have to use liquid cooling. Okay. So we will later discuss one more accelerator. There also it uses liquid cooling. That time I will explain how we actually do liquid cooling. So it's very interesting idea, right? How do you do liquid cooling? And then they do liquid cooling with which liquid? Which liquid they can use? Water. They do it with just water, right? So That's very, very interesting. They don't even use like there are some special liquids which are very inert, but they do it just with water. So that's very interesting. Okay. Now this is the supercomputer. I will skip this part. Now die size, it's very small die, right? Because it's just for inference, it's a very small power consumption. Here it is much higher area. Clock rate, again, this is just 700, very, very low. Here it is much higher. Here it is GPU runs at much, much higher. Now chip technology, here it is 20 nanometer. Here it is, we have not specified the exact feature size, but here they say more than 12 nanometer. Maybe probably it is 16 nanometer. Okay, it is 16 nanometer. Now this is the total memory size. Here it is 28 megabyte on chip. Here it is 32. Here it is again 32. So, and here the off-chip memory, that is the DRAM. DRAM here is 8 gigabyte. Actually, this is not megabyte. Actually, so there's a mistake here. That is GB. And here it is 32 GB. Here again it is 32 GB. Now memory bandwidth. Here it was just 34. Now you can see this is the biggest bottleneck, right? You can imagine how much bottleneck it will become. Whereas here you get 700 and 900. So see, when you see this figure 900, you have to always remember this 900 is not the bandwidth for a single port. This is the bandwidth of this port plus this port plus this port plus this port. To add their bandwidth, that is how you get this 900 number. Fine. So whenever we show this throughput values or bandwidth values, remember this is the aggregate bandwidth. So each of them will give you certain bandwidth, right? That could be, for example, around 225, right? So when you add 225 multiplied by 4, then you get this number 900. Okay. Here MXU size is 256 cross 256. Here you remember, right? Tensor core has 4 cross 4. That's how this number 4 cross 4 is coming. Here it is just 1 core. Now one host can connect to 4 chips and so on. So all these numbers are there. Here every core has 2 MXUs and we have 2 cores per chip. So here we have 4 MXUs. Here we have only 2 MXUs. Here we have just 1 MXU. Okay. So here that number is there. So please spend some time on this slide. If you have any immediate question, please ask me. No questions? Everything is clear?